Section 10.5 is on tangents. A tangent is a line that intersects a circle in exactly one point, and that point is called the point of tangency. So in this diagram here, I have circle P, and line L is tangent to the circle at point A. In other words, this line touches the circle in exactly one point, and that is point A. Here's a theorem related to tangent lines. A line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So, if line L is tangent to circle P at point A, then segment PA is perpendicular to line L. And conversely, if segment PA is perpendicular to line L, then L must be tangent to circle P at point A. In other words, a tangent line is perpendicular to a radius drawn to that point of tangency. So here's a couple examples. We need to determine whether segment AB is tangent to circle P. Well, if AB is tangent to circle P, then angle PAB will be a right angle. So in other words, is angle A a right angle, or looking at the bigger picture, is this triangle a right triangle? To show that, we're going to use the Pythagorean Theorem, and I realize that since PA is a radius and it is 15, PC is also a radius and it is also 15. So we need to ask ourselves, is PA squared plus AB squared, notice those are the two legs of the right triangle, equal to PB squared? And that's the hypotenuse. So PA is 15 squared plus 36 squared equal to, now the hypotenuse is 15 plus 24, or 39 squared. So grabbing your calculator, 225 plus 1,296, is that equal to 39 squared, which is 1,521? And yes, indeed, they are equal to each other. Therefore, segment AB is indeed tangent to circle P. And the reason I know that AB is tangent is that this is a right angle. Oops. That this is a right angle, and I show that that's a right angle because the Pythagorean theorem works on that triangle. So in this case, we're given that AB is tangent to circle P at point A, and we need to find x. Okay? So we know that this is tangent, so I know that this is a right angle, and I'm seeing a right triangle, so I need to use the Pythagorean theorem again to figure out x. So one leg of my right triangle is x, the other leg is 24, and the hypotenuse is x plus 16. So I can say the leg squared, which is x squared, plus 24 squared, which is the other leg squared, equals x plus 16 squared. Or x squared plus 576 equals, now be careful here, the quantity x plus 16 squared means x plus 16 times x plus 16, and you need to FOIL that. You can't just like distribute this exponent to both of those and say that's x squared plus 16 squared. No, you actually have to work it out. You have to actually FOIL it. So something like this. So take the time to do that, and you'll get x squared plus 32x plus 256. In my equation here, I have an x squared on both sides, so if I were to subtract x squared from both sides, that would disappear. That makes solving this a lot easier. Let's subtract 256 from both sides, and I get 320 equals 32x, and dividing both sides by 32, x is equal to 10. So in this problem, x is equal to 10. The radius of this circle is indeed 10. Here's another theorem. If two segments from the same exterior point are tangent to a circle, then the segments are congruent. So here we have circle P with point C outside the circle and tangent lines drawn from C to point A and C to point B. This theorem says that if those two lines are tangent, then those two lines are congruent to each other. So if AC and BC are tangent to circle P, then AC is congruent to BC. Let's try an example with that theorem. So it's given that AC and BC are tangent to circle P, and we need to find x. Well, I know that AC and BC are going to be congruent since they are both tangent to the circle and they intersect at a point outside the circle. So I can say 4x minus 3 equals 3x plus 2, or x equals 5. I like to think of this as the ice cream cone theorem, because a circle with two tangent lines drawn to an exterior point looks like an ice cream cone. A polygon is circumscribed about a circle if every side of the polygon is tangent to the circle. So here we have triangle ABC, and it is circumscribed about circle P. The word circumscribed literally means written around. So triangle ABC is written around the outside of circle P, and it touches circle P at these points of tangency. That would be D, E, and F. One other interesting thing is we can kind of tie in the previous ice cream cone theorem. If we look at just the circle and tangent line DB and tangent line EB, I know that these two are going to be congruent, because if you ignore kind of what's going on at A and C, you can see the ice cream cone. Also, FC is going to be congruent to EC, and DA is going to be congruent to FA, because those are points of tangency and tangent lines that meet at a point outside the circle. So here's an example. We have triangle ABC, and it is circumscribed about circle P, and we need to find the perimeter of triangle ABC. And we're given some information here, and I'm going to go ahead and note that on my diagram. So AB, this right here, that's a little crooked. That's a little better. AB is 8 units long, AF is 2 units long, and CE is 10 units long. That's the given information. Now, what can I fill in? Well, if AF is 2 units, AD is also 2 units, because those are two tangent lines that meet outside the circle at point A. Well, if AB is 8 and AD is 2, subtracting DB has to be 6. EB is another tangent line, which is congruent to DB, so that's 6. And up here, CF and CE are tangent lines, so CF is 10. So now to find the perimeter, all I have to do is add those up. 10 plus 10 plus 2 plus 2 plus 6 plus 6. And the perimeter of this circle is 36 units. I'm sorry, the perimeter of the triangle is 36 units. So that's the end of the lesson. Remember what a tangent line is. It intersects a circle in exactly one point. It is perpendicular to a radius drawn to that point, and two tangent lines that meet outside the circle are congruent.